go from current slide there. All right, any questions? Did you have one, or you were just looking for those to sample? Hey. You are? Okay. All right. Remind, huh? A little louder. Smith? Is that what, okay. I was listening for a first name. We had to do a, what do you call it? No-show report, but your name wasn't showing up yet. Have you finished all the?
Yeah, I'll check with them. I'll check with them.
You ought to check with
yeah.
our business office or somebody.
Okay.
And remind me.
Mason.
Okay, Mason Jasmine, right?
She looked like a Jasmine.
Yeah, okay.
We get Jasmine.
All right.
The Jasmine sit right here. She said her grandfather passed. She's not coming.
Oh, I'm so sorry. Okay. So, yeah. See, the Jasmines even sit in the same area. Okay, no, right. Okay. Yeah. And then I got a Janice, too. Okay. Well, I thought jasmine were sweet flowers, weren't they? Yeah, okay. So I won't answer that question. Okay. All right, let's go with any questions before we get started today. We are now recording, by the way, and we recorded all that. So, okay. Any questions? All right, where we left off last time was in Chapter 8, Section 8.2, Power. And we were at the top of page 211, getting ready to do example 4. Okay? And here's what example 4 says. A machine is designed to perform a given amount of work in a given amount of time. And what is work divided by time?
I'm sorry, what you said?
What is work divided by time? Someone said it? Power, exactly. Power. Okay. A second machine does the same amount of work, but in half the time. Find the power of the second machine compared to the first. So this one doesn't have any numbers, but we know from what they say here. Okay. Example 4, top of page 211. Okay. All right. Let's call the first one machine 1. Okay. Machine 1 is designed to perform a given amount of work, so that, let's call it work 1. Okay. In a given amount of time. Let's call that time 1. Okay. A second machine, we'll call that machine 2, is designed to do the same amount of work. So this work 2 is equal to work 1, and let's just call that work. Okay? Same thing for both of them. Okay? But it does it in half the time. So 1/2, let me write it this way. Okay. T2, the time it takes machine 2, is exactly half the time it takes machine 1. So 1/2 of the time for machine 1. So it says find the power of the second machine compared to the first. Okay, so the power for machine 2 is the work, same for both, W. What's the relationship? Work and time divided by time, which would be the time for machine 2 was 1/2 of time 1. Okay? Now, when you divide by a fraction, how do you do that? Remind me. Multiply by what? Yes, the reciprocal. So if you have 1 divided by 1/2, which is what we have here for our coefficients, right? Okay, that would be the same as 1 times 2/1, right? So that would be 2. So this would be twice W over T1, which of course is the power for machine 1. So machine 2 has twice the power that machine 1 has. Why? It does the same work, but in half the time. So it has to have twice the power. Okay? Does that make sense? Thus, the power is doubled when the time is halved, because that's an inverse relationship. Time to power. Make sense? Whoops. That's 2 times power 1. I'm sorry. I left off my 2. Okay. Example 5 is a bit more quantitative, a little less qualitative. But I'll let y'all finish that before I clear the screen. Anyone still writing? Yeah. Okay. Okay, everybody got it? Oh, you still writing? Everybody got it? Okay. Okay, example 5, the bottom half of page 211. A motor is capable of developing 10.0 kilowatts of power. So this is the power for that machine. The question is, how large a mass? What is the mass? Okay. Can it lift okay 75 meters? Okay, now what would that be? That's a distance. Now let's see what, I think they use S for distance, don't they? Okay. So that's going to be our distance S in 20 seconds. What's that a measure of? That's your time. So I need some formula that relates power, mass, distance, and time. But break it into smaller pieces. What's our power formula? Power is equal to work divided by time. So there's the time, there's the power, and there's the time. So is there some formula that or equation that represents work as a combination of mass and distance? What is the definition for work? Force times the distance. Okay, so that gets a step closer. We've got our distance in there now. Now, next question, is there a formula and an equation that relates force to mass? Especially if you're lifting the mass. What force are you dealing with when you're lifting something? Okay, what do you mean by total force? What specific force are you dealing with when you're lifting a mass? Okay. If I told you you had a choice of lifting the bottle or lifting the table, which would you choose? Really? Why? Oh, the weight force. Exactly. So what is weight force? Force due to weight is what? Newton's second law tells us force is what? That's total force, by the way. But mass times acceleration. And weight is dealing with what acceleration? Which acceleration are you dealing with? Especially if you're here on Earth. Gravity. And what is that? That's G times S divided by T. All right. Now we've got every piece of the puzzle. We got power, mass, distance, and time. We threw in a G for good measure. We know what that is. Okay?
So you said the S in the book, they use it for
distance. Yeah. They also use S for seconds, like But that's the unit second. The parameter s is distance. Now, I asked you that, and y'all said yes. Let me make sure that is right. Yeah, FS. Yeah, that's what they use, yeah. Okay. Now, we got two choices here. Here we have an equation that relates power to mass, gravity, acceleration due to gravity, distance, and time. And we're looking for the mass part. Now, you have two choices. You can either plug in the numbers and then solve for the mass that you don't know, or solve for m while you still got letters there, and then plug in the numbers. I call it chug and plug or plug and chug, whichever way you want to do it. You want to solve for the letter first, moving the other letters around, and then plug in the numbers, or you want to plug in the numbers now and then move them around, solving for the mass. It doesn't matter. Get m by itself. I like the idea. So what I'm going to do is move the p over here so it's closer, okay? Equal on this side or equal on that side, it doesn't matter. And we're wanting to solve for m. So what are we going to have to do to solve for m? What do we need to get out of the way? Okay, how do we get rid of the gravity? Divide by gravity, so we'll divide this side by gravity. That'll get rid of gravity. Which, S? Is that what you're saying? Yes, we'll divide by displacement. So we'll divide that side by displacement. That gets rid of displacement. Yeah, but we got something else. How do you get rid of the time? Multiply by the time. So we'll multiply by time here. That gets rid of time here. So that gives us mass is equal to the power times the time divided by acceleration due to gravity times the displacement. Whoa. Okay. So let's plug in. We know all of those, don't we? Power is, whoa, wait a minute. Distance is in meters. Mass, we'll have to figure out what that's in. Times in second. The power is in kilowatts. Do we really want to use kilowatts? What do we want to use? Watts, okay? So how many watts is 10 kilowatts? You may know that automatically, or we may have to do a conversion. Which do you want to do? Second? No, wait. Kilo means 1,000. So this would be 10,000 watts, right? Kilo means 1,000. So this will be 10,000 watts. Okay, now wait a minute. I don't see watts in any of our other units here. What is a watt? What's a watt? Okay. Anyone remember? And you can sort of base it on this thing right here. It's work divided by time. So what is work? What unit? Ladies?
Oh, work is what, Jewel?
Joules, yes, okay. Diamonds, okay. Joules.
I'm looking at it. Just want to say it.
Okay.
Because you're doing this.
Diamond. Diamond's our girl's best friend, okay? 10,000 joules per second. But I don't see any joules in this thing. So how do we define a joule? Well, you can get that from this one. How is a joule defined?
By displacement.
Force times, yeah, a displacement. So that would be how our force is measured. What's the unit for that one? Sir Isaac? Newton, okay. That would be Newton meters per second. Well, we still don't have any newtons here. This is just to get you used to doing the thing. You don't have to do it this long if you don't want to.
I prefer to do it the way book.
Okay. This is 10,000. What is a newton? And this right here suggests that. No, that's mass. These are your parameters here. Mass times acceleration, right? And what's your unit for mass? Kilogram. So it'll be kilogram acceleration meters per second squared times your meters. Okay, there's another meter in there. Okay, because force times that. So there's your numerator. That's what your power is. Okay, so let's come down here and put that in. That's 10,000. Okay, kilogram meter per second squared times meters. Multiply that by your time. What was your time? 20 seconds. 20 seconds. Now this second right now, it will wipe out one of those two second squares down there. One's in the numerator, one's in the denominator. So we're okay there. All right. Divided by acceleration due to gravity. Well, let's not do that one yet. Okay. Let's not do that one yet. Let's leave it like it was. Seconds. Yeah, okay. Okay, second squared. Okay. I've got a reason for that. What is G? Anyone remember that?
Oh, G is gravity.
And what's that? Acceleration due to gravity. What is that? A little louder. Did you say? This is, where do you get 75? Acceleration due to gravity in the SI system.
Oh, is it the 9 point?
That's it. 9.80 meters per second squared. That's why I wanted to keep the meters per second squared here, because they can cancel out down up there. Okay. This is multiplied then by your displacement. Okay. Seems like something's missing here. Okay, and your displacement S was, that's your 75. 75, oh, that's the 75 you look at. And that would be meters. Okay, I've got a problem here, folks. Power is force. Oh, yeah, wait a minute. Okay. I can see that the M's are going out here. Oh, wait, no. Okay. I sort of bite something up here. I threw an M in there that doesn't belong. Okay. I think. Let's see. It's power times time divided by acceleration times displacement. That's what your mass is. Okay? Power times time divided by acceleration due to gravity and your displacement. Oh, I know where I messed it up. This had an extra displacement in it. Yeah, well, we got that. Meters. Okay. No, we got that right. Displacement. Okay. All right. I've lost some units here. Power. I don't think I put down all my power units. Yeah, here it is. That's where I'm missing. 10,000. There was that. I knew it was there. There's the meter. 10,000 kilogram meter per second squared meter. Okay. That is what your kilogram meter per second meter and then per time. I forgot that. Yeah. Per second. That's the other one. So this second cancels that one out, and this meters cancel that one out. I left off the units from here. There I had Newton meters per second, the Newton to kilogram meter per second squared. I left off my other per second here and the meter there. So, yeah, we got them in there now. Whew. All right. That leaves us with kilograms. All right. So take your calculators, and it's 10,000 times 20, which will be 200,000, divided by 9.8, and divide that by 75. And that should give you a number with the unit remaining kilograms. Yeah. 10,000 divided by 20, multiplied by 20, divide that by 9.8, and then divide that answer by 75. Or you could put, is what? No, this is a time sign. That's 20 right up here, 20 seconds. I really should have put 20.0 seconds just to show you we still had the significant digits. Well, let me get that out of the way first and then do times 20.0 seconds. Okay. Okay. Now, there's two ways you can do this. It just depends on how you like to plug it in. You can do 10,000 times 20, that would be 200,000. Divide that by 9.8, and then that answer divide by 75. Now, if you don't like doing it that way, you can do 10,000 times 20, just like before, 200,000, and then divide that, but if you're doing the whole thing, open a parentheses, then do 9.8 times 75, close the parentheses, and hit equal. Either group that denominator together or divide them rather than multiply. One or the other. You're going to multiply them together, put parentheses around them. So either way you choose to do it, that'll do it for you. Got it?
Yeah.
What you get?
Hope it's right.
Okay, what you get?
272.10.
A little louder?
272.10.
272.10, and that would be kilograms. Let's see. Well,
Something ain't right.
wait a minute. $270. Okay, you got it right. The only thing is, notice here, 3 digits, 3 digits, 3 digits.
Okay.
Somewhere else I thought there were 3 digits, so we round it to 272. Don't go any further, kilograms. And that's exactly what they got in the book.
Really?
Yeah.
Hold on.
Flip the page. They only took you so far.
Oh, okay. I see. No
See-
wonder I was getting confused.
Yeah.
Okay.
Okay, you see, what they did was string it out, your calculations, one after another after another. We, by choosing to solve for the mass to begin with, we put them all together. So either way you want to do it is fine, okay? You can string it out and do step by step by step, or the way we did it here was put all of them down. We did all our stepping with the letters and then figured out what the answer was. So both ways work, whichever you see best. Yeah, that'll be perfectly fine. But you see, she'll get the same answer. All right. As long as you take the right steps, okay? On front end or back end, whichever you do. All right, let's move to example 6. All right, to erase? Okay. Now, a pump is needed to lift 1,500 liters of water per minute. So this is 1,500, and there's a line over the first zero, meaning that's significant. The last zero is not. And this is liters of water per minute. Okay? Liters per minute. A distance of 45 meters. So 45.0 meters, that's going to be our S. Okay. What power, we're looking for power here, and it says in kilowatts. Well, we'll go back and figure the kilowatts later. Must the pump be able to deliver, and here they tell you something, 1 liter of water has a mass of 1 kilogram. Okay, and that's exact. So you can put as many decimals and zeros with that as you want to. So don't think that's limiting to one significant digit. It's not. That's an exact measure. 1 liter of water is 1 kilogram. 1.0 liters of water is 1.0 kilogram. 1.00 liters of water is 1.00 kilogram. You can put as many significant digits with it as you want to. That's your conversion factor. Okay. So, what we have here, since 1 liter is 1 kilogram, that means you're lifting how many kilograms? 1,500 sorry, I'm so used to putting vector notation. This is not a vector. That was a line, and I just got carried away. I might say, why doesn't someone carry him away? Never mind. Okay. Ah, there we go. This is kilograms per minute. Okay. Now, we're looking for power. Remind me what power is? Work divided by time. You know, we've got our per time here in the per minute, so we don't have to worry about time. It's going to be carried along here. But what is work? Remind me what that is? Force times a displacement, a distance over time. And the time, remember, is already taken care of. So this S is displacement. That's why I don't like to use S. But anyway. But what is force? Mass times, acceleration due to gravity. This is the force due to weight. Acceleration due to gravity times displacement over time. Well, what we've got here, this thing right here, is a mass per unit time. So that's your mass per unit time, is this right here, 1,500 kilograms per minute. Okay? Oops. Whoops. Our calculations, especially for power, is based on per second. So we got to change this 1,500 kilograms per minute into how many kilograms per second. So how are we going to do that? Okay, well, let's, we want kilograms per second, because everything else is going to give us seconds. Okay, power is measured in seconds per second. Watts are measured in joules per second. So What are we trying to change? We don't want to change kilogram. That stays kilogram. We're trying to change minutes to seconds, right? Now, here's our conversion factor. Remember how I told you how to do these? Always put the units in their place first. The first line's for numbers, the second line for units. So we want to put the units in the place. Which unit is going to go where? Not kilograms. Kilograms just like we want it. Don't mess with kilograms. We're changing minutes to seconds. So one of those got to go on top, one of them got to go on the bottom. Which goes where? Which one? Which one? They're both times. Which? Minutes or second? Which one goes on top? Minutes on top and seconds on the bottom. That way the minutes will cancel out here and you're left per second just like you need it to be, right? So now you answer the question, how many minutes in a second or how many seconds in a minute? Which way? 60 seconds is 1 minute. And guess what? You can add as many zeros to this as you want to. That's an exact conversion. 1.00 minutes is 60.0 seconds. So you can put as many zeros with it as you want to. What's that? 10 minutes to 600 seconds. Exactly.
10 minutes to 60.
Yeah.
I never knew that.
Yeah. Okay. All right.
100 minutes is 6,006.
Right. Very good. Okay. So what we do here, yeah, what we do here is you can wipe out one of these zeros with one of those. That's easy to do. And do 150 divided by 6. Or you can do 1,500 divided by 60, whichever you want to do. What would that give you as the answer? 1,500. Is that again? 25, and we'll put a 0.0 there, kilograms per second. Okay? So we got it in from liters per minute to kilograms per minute, because we knew a liter is a kilogram, and then we divided that by 60 to get how many kilograms per second. Okay? So this will be 25.0 kilograms per second times the acceleration due to gravity, which is 9.80 meters per second squared, times your displacement, 45 meters, 45.0 meters. Okay? I think we're ready to roll now. 25 times 9.8 times 45. All these are in the numerator, so you multiply them together. Right. 11,025. Okay. That's what you got, 11,025. Okay, let's see what our units are. What's a kilogram meter per second squared? Nope, that's a Sir Isaac. Newton. And a Newton meter is a joule. And a joule per second is a? No. Joule per second is a what? A watt. Yes, okay, good. That's a watt. Now they wanted it in kilowatts. So how do we get 11,020? Huh? Yeah, you just move your decimal 3 places. Okay, so that'd be 11 point, but we only need 3 digits. So you count 1, 2, 3, 11.0. Look to the right. The 2's less than 5. Drop it. Right? 11.0 kilowatts. Okay. That's exactly what we want. Oh, and look at that. The book got it too. Good for them. Okay? Does that make sense?
I see where you're coming from.
Okay. Southside Birmingham. No, never mind. Okay. All right.
No, man.
Homework exercises here. Do either 1 or 3. Those are very similar. Or both of them if you choose. And then do some of the other odd ones. Okay? I would do some that they're looking for different ones, and that would go anywhere from 5 to 25. What's that? I can't hear you by hearing. So. Why? Why would we want to do that? And cheat you out of your tuition dollars? I'd never think of it, okay? I don't want to cheat you out of anything.
Because some of these questions I notice on tests kind of tricky.
Yeah.
Oh, really?
They are.
It's just the wording of them. You got to really word it. I mean, it's...
Okay. Now, and by the way, anytime you want to ask questions, you can. That's why I started off. Are there any questions? So you can ask questions on, clarification or...
The only one that's really confusing to me that I didn't get in chapter 5 was the third law. Newton's third law is the count. It's like complicated. I don't know if you had one of them on the test.
I don't think it was. I don't remember one. Well, kinda. Number 9 is sort of like
I was
that.
about to say, I thought it was number 9 because I tried to figure that one out for so long, but I did my best.
Well, remember, Newton's third laws are acting on two different bodies. If I push on the desk, the desk pushes on me. The amount of force by which I push on the desk, same force the desk is pushing on me. So if you figure out going one way, it's the same, just opposite direction. Is that helpful?
Yeah, but is it like a formula that you to work the problem with?
Well, you just use the formulas for forces or whatever.
Okay.
Let's see. That one is, they give you a mass, they give you two masses.
Right.
And they give you the Newton. Oh.
Yeah, now you see.
Yeah. But what did I just say?
I figured it out. I think I figured it out.
Right. Okay. What is it that's equal in Newton's third law?
Force.
The forces.
Yeah, force.
And they gave you a force. Guess what? Never mind.
Yeah.
Think on that. Okay. That finishes 8.2. Any questions? And any other questions? Anytime you got one, ask. Okay.
I think I have questions once I work some of these out.
Okay. All right. Let's move on to 8.3, which is energy. And guess what? Work and energy are just two forms. They're kind of two sides for the same coin. Okay? In fact, here is their first sentence here. Energy is defined as the ability to do work. So let me start a new page here. Can I erase this? Is that okay? Okay. I went to erase and I hit the wrong button. Okay. So let's start with that definition. Energy is the ability to do work. So how much work you do is how much energy you expended. How much energy you expend, that's how much work you've done. They have the same units. They're measuring the same thing. One is the energy it took to do it, and one's the work that came from it. It's measured the same way. Now, the deal about energy is there's so many stinking forms of energy, okay? One of these is called potential energy. Ooh, I can't write. Okay. Potential energy, I'll give you the definition. Well, I'll write it out the way they did. This is why it's called potential, stored energy, okay? And it says due to either one of two things, internal characteristics or its position. I'm going to abbreviate, okay, characteristics or its position. Now, most of the time we're going to be dealing with position, but I'll talk about stored characteristics as well. Okay. If I were, could I borrow someone's foot? Okay. If I were to lift this book, you want to do the other foot? Okay. All right. If I were to lift this book way up here, does it have any energy? It's not moving. It's just sitting there. But if I were to drop it on his good foot, I'm not going to. Do you think he would suggest that it did have some energy? Absolutely. If I dropped it from here, less energy than if I dropped it from here, right? That's the stored energy of its position. Now, how did it get stored? I did work lifting it here, storing energy of position, its potential energy. Then when I released it, that's when it did work on his foot. Okay. Which I'm not going to do because he already has one bad foot. Okay. So that's the energy of position. Now, let me tell you sort of what they're talking about by internal characteristics. You see the little green leaves on that tree out there? That's a holly bush, so that's why it still has some green leaves on it. What are those little green leaves doing? What do they typically do? Second? Move with the wind is that what yeah. Well, they do that. But what is the purpose of those green leaves? What's that? Ah, yes. Okay. They do release oxygen. What process is that called, the releasing oxygen? Has to do with light. Photosynthesis. Exactly. Now, what is being synthesized?
It's the oxygen, right?
Okay, oxygen is being released.
Yeah.
What is being synthesized? In other words, that's made, huh? Carbohydrates, you're absolutely right. You see those little green leaves there have little pores, they're called stomata on the bottom side, some on the top, but mostly on the bottom side. Stomates, another thing for it, and they pull in carbon dioxide from the air. Now those roots out there, this year especially, sucking up that water. We've had plenty of water this year, right? Pulling up the water, combining with the carbon dioxide, and those little green leaves, what makes them green is a substance called chlorophyll. And chlorophyll is the magical ingredient that changes, combines, synthesizes carbon dioxide and water and makes carbohydrates. Hydrogen, oxygen compounds, which in the process releases some oxygen. Okay? I know you're not all this interested in the chemical formula, but here's what it is. You have CO2, carbon dioxide, plus H2O, water, and that produces C6H12O6, I believe it is. C6H12O6. You don't need to. I'm just explaining this to you, okay? Now, there's also some oxygen released. O2, oxygen's a diatomic gas. Well, to get 6 over here, you'd have to have 6 of these, right? And to get 12 of these, you would have to have 6 there, right? Okay? Well, how many oxygens do you have? This would be 12 plus 6 is 18. Well, this is 6, so that means the other 12, 6 oxygens are released. Thank you, green plants, because if those green plants weren't here releasing oxygen, we don't live, okay? Because our atmosphere would be all nitrogen and carbon dioxide. There wouldn't be any oxygen for us to breathe. Thank you, green plants. You're releasing all this oxygen. Okay, why has this got anything to do with potential energy? Well, if you notice here, the first thing, stored energy to internal characteristics. This bonding of the carbon with the hydrogen with the oxygen into the carbohydrates, what do we use carbohydrates for? So, yeah, in our food, and what does especially the carbohydrates give us? Energy, exactly. The proteins build muscles, the carbohydrates give us energy. So that's the whole process. This is storing the energy in this chemical structure here in the little green leaves, and that is stored potential energy for us to later eat, like he's getting ready to go to, and so he'll have some energy to move around on his little bicycle, cycle. It's not a bicycle, but a cycle. Okay. Take care of that leg. Okay. I've got an expert backer. Okay. All right. Good deal. Okay. That's another form of chemical, potential energy. Stored chemical energy. Stored, gravitational potential energy due to position. We're going to deal mostly with the position one. This was just to refresh your memory of simple biology and chemistry of how we do what the little green leaves are doing for us. Okay? They give us food for energy, and they give us oxygen to breathe so we can use that energy. And by the way, we oxidize the carbohydrates, and the energy that's stored in those bonds, that's what we use, and then we breathe out carbon dioxide and water vapor. So there's the whole cycle again, going from stored potential energy of those chemical bonds, releasing them so we'll have the energy to operate. All right, but there's another form of energy. There are many other forms of energy. Another one is called kinetic energy. Now, I don't know if you remember back when we were talking about friction, I think we used the term kinetic there too. What does that mean? What is kinesiology? Second, it's the study of motion. So kinetic energy is the energy due to the mass and velocity of a moving object. Due to mass and velocity of a moving object. Okay. Now, when I was holding that book above his foot, I gave it stored potential energy. Okay. If I dropped it, then it starts speeding up. It had mass, quite a bit of mass, and it would start increasing its velocity. And by the time it reached his foot, from a high distance, that have a large velocity, that's a lot of kinetic energy. Now, if I dropped it from down here, it wouldn't have much velocity because it wouldn't have fallen very far, right? And the rate of fall is the acceleration due to gravity, 9.80. So all these things are tying together like that, okay? So the internal potential energy I already talked about is determined by the nature and condition of the substance. For example, gasoline, compressed spring, stretch rubber band, they all have internal energy. Gasoline, again, stored chemical energy. Same place that those came from, those little green leaves, only that was thousands of years ago, stored them chemically, and then over time that got buried in microbiology involved. The microbes broke down some of those, that leaf mulch and stuff like that, and changed the form until it formed crude oil that they pumped out of the ground and then refined to be gasoline. Okay. Gravitational potential energy, that's the one of holding something up and then releasing it. Determined by the position of the object to a particular reference level. Gravitational potential energy needs to have with it some type of reference level. When I was holding the book above his foot, I was counting either his foot or the floor as the zero reference level, because that's what I was holding up that far. However, if I was holding it just above the tabletop, that would be my reference level, because it's not going to fall any further than that. But if I held it out the window, then it would be the ground out there. Especially if we're on the second story, that would still be, okay? If I counted sea level as a reference level, then I'd have to figure out how far we were above sea level, but I'm not dropping it above sea level. So anyway, you need a zero reference level so you'll know how much energy you have, because it all depends on how high it was. Now they use the symbol E sub P. I'm sorry, I can't write. E sub P for potential energy. Okay? But this is one particular potential energy. This is gravitational potential energy. So it depends on the mass, the acceleration due to gravity, and the height. So now they're using height where before we used S for displacement. Okay?
You said it must have 0 reference level.
Yeah, you have to indicate what your reference level is. When I say,
No, I was just trying to write down.
yeah, okay, yeah. When I hold the book here, how high am I holding it? Well, it depends on where I'm going to drop it. How high above the table, how high above the floor, how high above the ground, or if it was up on the second level, yeah. The 0 reference level says what I call as low as that thing can go in this particular problem. So if I was dropping to the floor, it's going to be the floor. If I was only dropping to the tabletop, I could use a tabletop as a 0 reference level. You determine that ahead of time. What's the lowest level this is going to go in this problem? That's my 0 reference level. And I identify that, and then I don't worry about anything below that. Okay? You can set anything to be it. You can set sea level and then subtract off. This is so many feet above sea level, so the difference. The big deal here, this really should be a change of height. In fact, that's how I like to write my, how I like to write this, rather than potential energy, I like to call it GPE, gravitational potential energy, meaning gravity's involved. And then I would call this mg times your change of height. How high is the difference between where I'm holding it and where it's going to land? And that takes into account the 0 reference level. But because this book uses this formula, we'll use it. But just understand that height is how high above the 0 reference level, where we're going to let it fall. So E sub P is gravitational potential energy. We just said there's other types of potential energy. All right. Let me see. This is it Vante? Okay. All right. Now, did you get, I forgot to ask the rest of you this, did everybody get the test from last time? Did you get one? You did, okay. I couldn't remember. Okay. All right. What's that? Only if you're through with it. Okay, yeah, I'll take them anytime you're through. Okay. All right. And the H in the book is height above the reference level. So that's what we're talking about there. Okay. So let's do example 1, top of page 215. Can I erase this? Because I need more room to write. Okay. A wrecking ball, I'll do the chain here. There's your wrecking ball, okay? Of mass 200 kilograms. The mass of this wrecking ball is 200, and that last 0 is significant, meaning the one in between is significant too, kilograms. Pretty massive ball there. Is poised 4 meters above a concrete platform. So the height here, I'm going to call it h because that's what they call it. H is equal to 4.00, pretty precise measurement, meters above the concrete platform. Okay? Whose top is 2 meters above the ground. So here's the ground here. So this is 2.00 meters above the ground. Okay? With respect to the platform, so if it's with respect to the platform, this will be my 0 reference level. The platform will, not the ground, the platform. So with respect to the platform, what is the potential energy of the ball? What is the potential energy? They call it E sub P. I like to call it gravitational potential energy, GPE, but whichever. What was that formula? Second? mgh. Okay? And the mass of the ball was 200 kilograms. And G is 9.80. What units? Meters per second squared. Okay? And the height above the platform was 4.00 meters. What's that? Okay. Pull out your handy dandy calculators. Multiply 200 by 4 would be 800 times 9.8. And what do you get? A big number. Close to 8,000. 7,840 what units? Kilogram meter squared per second squared is a joules. Okay? Yeah. If you don't like that big a number, you could make it this smaller number but a bigger unit. What would that be? No, don't change the unit. No. Just move your decimal. Kilojoules, exactly. 7.84 kilojoules. Now, we don't really use kilojoules that frequently, but you could. It's perfectly fine. All right, let's see what they got. Whoa! Wait a minute, I'm sorry. I looked at the wrong line. 7,840 joules. That's exactly. But that was the A part. Let's look at the B part. With respect to the ground, though, what is the potential energy of the ball? Move the ball up from in front of the platform, move it over the ground. What will change here? E sub P. Yeah, 4 plus 2 is 6. So your mass is the same, the G is the same, but now the height to ground is going to be 6. So that would be 200 kilograms times 9.80 meters per second squared times, now it's 6 meters. Now this is your zero reference level. It's moved down here. So it'd be 6.00 meters. Okay? So that'd be 1,200 times 9.8. 11. Someone punch it in your calculator. 200 times 9.8 times 6. 11,760. Is that what you said? That would be what unit? Kilogram, meter squared per second squared? Joules, exactly. Now we got a little problem here because they only had 3 digits, 3 digits, and 3 digits. Everything was 3 digits, even the 9.80 is 3 digits. You got 4 here. So, well, you could do that, but let's first make this, round it to 1, count off 1, 2, 3 digits, look to the right. That's a 6. Greater than 5, that means you up this one by 1. 11,800 joules, or how many kilojoules? 11.8 kilojoules. Either one of those is acceptable, and that's what they do. Okay? So they rounded sort of early. So that's how you do potential energy, gravitational potential energy, mgh. The mass times the acceleration due to gravity that's pulling it downward times the height through which it's being pulled. Okay? mgh. Okay? Ready for a clean slate? Can I clear? Yay or nay? Okay. All right. Here we're going to go to kinetic energy. Now remember, what did we say kinetic energy was? Now I like to call it, say again? Yes, it's due to the motion. Exactly. So I bet you they call it E sub K. I like kinetic energy. They call it E sub K. I call it KE, but either one will work. What is this formula? Okay, if an object is moving, what does it have to have? It has to have a displacement. More specifically, displacement per unit time is called, see, I could be, I don't know, y'all probably don't remember Tim Conway. He played an old man, and he could move like this. He's moving, okay, or he can move, or someone else can move like that. What's the difference? You have displacement either way, but what's the difference? The speed, the velocity. That's what kinetic energy depends on, is the mass times the velocity. But it's not just mass times velocity. That's something else. This is, it's strange formula, 1/2 mv squared. That is your kinetic energy. Okay? Mass times velocity wouldn't give you energy, because mass is kilograms, velocity is meters per second. Kilogram meter per second is not a joule. You need kilogram meter squared per second squared. That means your velocity has to be squared. Kilogram is your mass, meter squared per second squared, that's velocity squared. But it's 1/2 that. Now you might say, where does the 1/2 come from? I'll just tell you this. Most of your equations in physics, when they have the main parameter squared, you'll usually have a 1/2 in front, or something with over 2. It comes from an integration constant in calculus. Y'all don't really need to know it, right? Okay, but expect it and look for it. 1/2 mv squared. Always has it in there. Where E sub K is kinetic energy, m is the mass of the moving object, and v is the velocity of the moving object. Okay? Now, for some reason, this book loves pile drivers. Okay? Y'all know what a pile driver is? Okay, have you ever seen at the very beginning of a building being built?
Only some of the little things that they hold.
Okay, now that's packing something in. That's sort of like it, but this is even before that. Okay? They dig out the foundations, but they want to put something to make sure it's going to be solid and not move and crack. Okay? They take the thing and just, it's a lot like driving a nail into wood. Only they're driving a big old pile, which is some sort of foundation, into the ground. And that's what a pile driver is. It's just whamming it and whamming it and whamming it into the ground. Before they build a bridge, they go out where the stanchion that's going to hold the bridge up, they wham and wham and wham something into the soil until you got something good and solid to build your bridge on. If you just build it on that sloppy soil there at the edge of the bridge, it's going to dry out sometimes and stuff, you're going to have a messed up bridge. So they drive a pile way, way down until they've got a really good foundation. Okay? Now in houses, they usually just dig a trench and fill it with concrete, and that makes the foundation. But big, tall buildings, they need something way deeper than that. So that's a pile driver. There's picture 1 in your book there on page 215. That's figure 812. Shows the relationship of energy of motion to useful work. The energy of the driver is its kinetic energy as it hits, and the driver strikes its pile, driving the pile into the ground. Work done is on the pile, force into the ground. The depth it goes into the ground is determined by the force applied to it. So, here would be your equation. If I can get my pen back. Okay, there it is. The energy you gave that in striking, you really make that thing go fast. 1/2 mv squared, that's the kinetic energy of the pile driver, drives it into the ground, and that with some force times a distance. Okay? There's your basic formula. And if you think about what the force is, earlier we had it mass times acceleration due to gravity. That's the weight force. This is a much stronger force than that, but that's the same units. And by the way, S is the same as H before, mgh. Only now it's some other force, but it's the same thing. Energy is energy. It's just you changing kinetic energy of the pile driver into the work done by driving the pile. So, can I clear this? Got it? Okay. Okay. Example 2. A pile driver with a mass of 10,000 kilograms. That's a lot of mass. If you've ever seen these things, they are really massive. 10,000 kilograms, that's the mass of the pile driver. Okay? Strikes a pile with a velocity of 10 meters per second. So, velocity of the pile driver, that's a P there. I was trying to think, what letter did I have there? That is 10 meters per second, right? There it is, yeah. 10.0 meters per second, okay? And all three of those zeros are significant. Only the one and the first zero and the second zero are significant up there, 3 digits, okay? So that's all they tell us. What is the kinetic energy of the driver as it strikes the pile? So what is the E sub K? What was that formula? 1/2 M V squared, exactly. Okay, so this will be 1/2. The mass is massive, 10,000 kilograms. Okay, times velocity, though, was 10.0 meters per second, but we're squaring that, right? It's going to make another big number. Now, just to save some writing here, I'm going to do 2 into 10 will be 5. So we'll call it 5,000, and we'll keep the unit kilograms. We haven't really changed the mass, but we'll keep it. But what happens when you square 10? Not 1,000. 100, exactly. You double the number of zeros, okay? So it's 100, but you also square your units. Meters squared per second squared, okay? And 100 times 5,000 would be 500,000. And what's a kilogram meter squared per second squared? Joules. Now that's a really big number, so you might want to write a little smaller number but bigger unit. That would be what? 500 kilojoules. Kilojoules. 1,000 joules. Okay. Instead of those last 3 zeros mean 1,000, make it kilojoules. All right. What did they get? Yes. They put 5.00 times 10 to the 5th joules, or 500, and I ought to put my bar over it, kilojoules, so you'll know that is a significant digit. Okay. Now, the B part of this question says, if the pile is driven 20 centimeters into the ground, what force is applied to the pile by the driver as it strikes the pile? So remember the formula they gave at the end, the E sub K was equal to the force times displacement. That would be work and energy, same units. And they just told us what we're looking for now. We've got the E sub K. This is, I'm going to write it all out, 500,000 joules. But what's a joule? Kilogram meter squared per second squared. Kilogram meter squared per second squared is equal to force. That's what we're looking for. And it said, how far did it drive it into the ground? Yes, the S was 20.0 centimeters. Whoops! This is in meters, that's in centimeters.
Multiply by 10.
Say again?
Multiply by 10.
Okay. Not quite. Let's do it. Okay, 20.0 centimeters. We're going to multiply it by something, and what we want to do is get it in what unit? Not centimeters, but meters. So we always put what first? These are for numbers, those are for units. We always put the units in their place. So what unit is going to go where? You got centimeters and meters. One goes on top, one goes on bottom. Which goes where? Second? No. If you put, yeah, on bottom because they need to cancel out. And that means meters on top, and that's where you want it because it's going to wind up on top on the other side, right? So now you answer the question, how many meters in a centimeter or how many centimeters in a meter? Anyone remember? Okay. Let me see if I got one. Oh, I do. What's this called? A cent. How many of these make a dollar? 100. 100 centimeters. Centi means 100. Okay? 100 centimeters makes a meter. 100 cents makes a dollar. So you match 100 centimeters to 1 meter. Okay? Now you see you divide, not multiply. So this is 0.200. See, you move this decimal 2 places, move that one 2 places, and that makes it 0.200 meters. So force times displacement, which is 0.200 meters. To solve for force, what do we do? Divide by 0.200 meters. Divide this by 0.200 meters. Now notice what happens with your units. Oh, everything cancels here. Here the meters, one of those cancels out, and that leaves you, well, now that's going to make your number even bigger because you're dividing by a small number. So 500,000 divided by 0.2 is 250,000. Is that a lot? Isn't it? 2,500,000, I think. Is that right? Now, what's the units for that? A kilogram meter per second squared? What's that? Meter squared per second squared. Newton! Wow, 2.5 million newtons. Okay? And that's how they do it, how they write it, is 2.50, because you got to have 3 digits. Times 10 to the, you know scientific notation? How many places did you move the decimal? 3, 6. 10 to the 6 newtons. That's how they wrote it. Okay? Now, you don't need to know this, but another way you could do that, 3 digits would be kilo, 6 digits is mega. Just think about megabytes, that's 1,000,000 bytes. Megajoules, so to speak. So that unit, and I never see this done, you could do it 2.50 meganewtons. Now, I never see that done. If you look at that, you think that's abbreviation for Minnesota. That's not what it is. It's meganewtons. But most of the time, they use scientific notation there. 10 to the 6th newtons. Very good. All right. Does that make sense? Can I erase it? Move on to the next one. All right. Okay. Oh, good. Okay. Oh, that's right. Okay. I was thinking we went till 7. We go to 6:30. Okay. Y'all remind me of that. You know, if I start going to, you will remind me? Thank you so much. Y'all are so kind to do that. Okay. All right. All right. I was looking and say, oh, we've done a minute and 14 an hour and 14 minutes and 15 minutes, and we still got an hour to go. How do we do that? No, half hour to go. All right, example 3. A 60-gram bullet. 60.0 gram bullet. What's that a measure of? Mass. That's another mass, and this is the mass of the bullet. Is fired from a gun with 3,150 joules of kinetic energy. So 3,150 joules. They just told you that's your E sub k. Okay? Find the velocity. We're looking for velocity. Okay? Now, there's a little something wrong with this picture. Okay? First, you tell me what a joule is. What does that break down to? Kilogram, meter squared, per second squared. That's what a joule is. And notice up here we got grams. We need those grams in kilograms so we can talk about joules. So how do we get grams to kilograms? Our good old conversion factor, don't we? Or what? Move the decimal how many places? 3. To the left, to the left. Okay. Sounds like a line dance, doesn't it? Okay. So this would be 0.0600 kilograms. Okay. Remember, kilograms the bigger unit. So if you're going from a number with a small unit, you're going to have a smaller number with a bigger unit. So that's why you move the decimal 3 places to the left. Kilo means 1,000, move it to the left. Or you could have done your conversion factor. We could have done it that way. I take it y'all like this way better. Okay, so now we got our mass in kilograms. And our kinetic energy was this. Well, what is kinetic energy? What's its formula? 1/2 mass times velocity squared. And we're looking for velocity. So what that means we're going to be doing, we have to isolate the v here. So we're going to multiply both sides by 2, right? To get rid of the denominators. We don't like denominators, do we? So multiply, get rid of them. But then we multiply this side by 2. Okay? So that gives us 6,300 kilogram meter squared per second squared. That's equal to, you canceled those out, divided those out, your mass times your velocity squared. Well, you're trying to get velocity, so what are we going to do next? Yeah, we already know the mass. Well, you could plug it in, or you could, to save some writing, divide by the mass here, and over here, divide by what the mass is, right? 0.0600 kilograms. See, the masses go out here. They've been dating. Okay, here the kilograms go out, and what you're left with is 6,300, which is already a pretty big number, divided by 0.06. This is going to be a huge number. So what is it? I'm going to do this. I'm going to cheat a little bit. I'm going to move that decimal 2 places that way, this one 2 places that way. That'll be 105. Whoops, I did it the wrong way. Did I? Yeah, I moved it the wrong way. No, I didn't. Yeah, what did you get? It's what? Say 105,000, is that what you said? Yeah, okay. 105,000, and that would be meter squared per second squared. That's velocity squared. But you know, I'm not really interested in what velocity squared is. I want to know what the velocity is. That's what I asked for. What's the velocity? Find this velocity. Okay? So how do I undo a square? How do you undo a square? Oh, sure you do. You take a, or you undo a square. What is 2 squared? 4. How do you go from 4 to 2? Take a, well, let's do it a little bit. What's the square of 3? 9. And how do you go from 9 to 3? You take the square root. Have y'all done square roots?
Oh,
Of course you do.
Okay.
That's how you undo a square. You take.
Like how I just look at that number and
No.
know how to undo the square number.
You have to take a square. Yeah, I'm going to use a. You're going to use a calculator. I'm not going to do that in my head. I will do this. I will pair these two, those two. Square root of. It's going to be something on the order of 300. See what you get. Square root of 105,000. Oh, I know it is.
It's a little, it looks like a division sign.
Yeah, with a little V in front.
Yeah.
A notch in front.
Yeah, I see that, but I'm trying to see. I don't know. It's like, I don't know if you're supposed to like.
You press it first, I think, then enter the number, and then
It depends on the
Yeah,
calculator.
the calculator. I'd have to figure out how to use the square root on here.
Okay. Oh, me.
I don't know. I see
Terribly
the
to be
square
old.
root symbol, but it's giving me like another symbol. See, it's on here, but I don't know, like, if I put it in, it gives
No, you have to do second. See, that's the blue thing, so you do
okay.
second that.
And then do that.
And
And
then
then
do
what's the
105,000. What'd you get? 324, right? I said around 300, didn't I? Okay. Is that what you got, 324? But we don't just take the square root of the number, we take the square root of the units too, and what would that be? Meter, take the square root. Meter per second, and that's a great unit for velocity. So we got 324 meters per second, and so did they. Good deal. Make sense? All right. Now, there's other kinds of potential energy other than gravitational potential energy. There's when you push on a spring, it's pushing back on you. When you push on the spring, it's storing potential energy. That's called spring or elastic potential energy. Or when you stretch a spring, it's pulling back. That's called elastic or spring potential energy. Okay? Robert Hooke, who was a little bit older, I think, than Isaac Newton, and they were both British, and they really didn't get along too well. They did at first a little bit, but then after a while, Newton zoomed past Hooke, and Hooke sort of resented it because there weren't many minds that were anywhere close to Newton's mind. And I think they had some problems. But anyway, that was along, and they did work together some. But anyway, he talks about spring potential energy. Hooke's law, they say, is going to be in section 12.2. I don't think we're going to do that. So if you want to look ahead, you could do that, but I don't think we're going to. So problem set 8.3. Do any of the odds, do either 1 or 3 or both. Those are fairly similar. And then do any of your odd numbers 5 through 21. There's a whole bunch there. Just pick out some of different types and work on those. Okay? All right. We still got time. Okay. So let's move on to 8.4, which is conservation of mechanical energy. Okay, we mentioned, huh? It's not all that long, is it? Okay, yeah, and that last one is really short. Yeah. Okay. Oh, we're having fun, right? Time flies when you're having fun. Okay.
I'm gonna go home and work out some of these problems.
That's
Yeah.
why I'm trying to pay attention now, so I can go back and write it, because at least I paid attention to know what we did.
Good. And then you can always watch the videos again too, Okay. All right. So in fact, rather than clearing this, I'm going to discard it and move finally to this one. This is the next slide. Oh, yeah. That was the last slide we had.
Wow, we've been going that long.
Okay, that was last time. And yeah. Okay. Yeah, there we go. Here is the slide we're on now. They love pile drivers, didn't I tell you? This is the one done by a crane, okay?
Is that what they're using for the new freeway?
Probably. They said they collapsed the bridge, the Red Mountain Expressway, didn't they, last weekend? Karen saw it, my wife saw it on her internet.
Oh, no, someone said they saw a picture of that they had just knocked the bridges down.
Yeah. So it's going to be about a year before we'll be driving those intersections again.
Yeah, and I have to drive. It's just too far to be driving.
I know. I had found what I thought was a good way to get here, and Monday morning, I found out a lot of other people found that was a good way to get here too. So I had to find another one. And then too, around UAB, they're doing so much construction, so you have to avoid the construction.
Just use your GPS everywhere you go, because your GPS will give you.
It'll tell you when
traffic and all of that.
Yeah. But the thing is, especially downtown, I don't have time to be looking at this and looking at the road and stuff. The 10 o'clock scholar. Okay. And let me guess, you're the other Jasmine, right? Jasmine? No.
Person.
Huh?
Last name
Kirksey. Latondria. Is that right? Okay, so good. She threw me off. She said, the other Jasmine sits here. So when you sat there, I thought it was, never mind. Okay. All right. We're just starting 8.4, which is on page 219, the conservation of mechanical energy. And what I was going to say, we've only talked about two types of energy. Potential energy, which could be gravitational, spring, chemical, or other potential energy. So many kinds of energy. Or kinetic energy, which is the energy of motion. The energy of potential energy is the energy of position or internal characteristics, whereas kinetic energy is the energy of motion. Okay? Now, this energy, we're talking about mechanical energy. And do they actually give? They don't give a subscript for it. So what I like to do is call it ME for mechanical energy. I thought they would do it E sub M, but I'm going to call it ME, mechanical energy. To me, that makes a lot of sense. How is mechanical energy defined? Well, here is the law of conservation of mechanical energy. The sum, which means what? What operation we're doing if we talk about a sum? Adding. The sum of the kinetic energy and the potential energy in a system is constant if no resistant forces do work. So in other words, mechanical energy is the sum of what the book called, I keep doing what I call it, the book calls E sub K, kinetic energy plus potential energy. Whatever your potential energy, gravitational potential, spring potential, chemical potential, whatever, if you've got mechanical energy, that's the sum of these two energies, okay? And this sum is conserved, meaning it does not change as long as there's no external forces acting on the system, okay? One of the classic examples of this is bowling, okay? I don't know if you're into bowling, but if you think about bowling here, what I do is pick up those balls, and that's a fairly heavy ball too, and I lift it giving it potential energy, but I also swing my arm, so I'm giving a force to it, but also letting it fall. So the combination of my force times displacement plus the change of potential energy, that gives it kinetic energy as it rolls down the lane. Well, the total here is the total there. There is kinetic energy, here is potential energy. Okay? That's how the law of conservation of mechanical energy, because mechanical energy is the sum of the two. Okay? Up here it's all potential, down there it's all kinetic. This plus 0 is equal to 0 plus that, so you're adding. Now, the pile driver, they love the pile driver here, shows that energy conservation. When the driver is at its highest position, and that's what they do, they raise that big heavy mass here up to the highest position. Now they have it in a sleeve so it can't get out of place in the sleeve, and they lubricate so this falls really easily. And when he lets it go, then it falls that height. They give that as H, I think. I can't read that. I think it's H. Yeah, okay. It falls that height. So the potential energy here, which is its maximum here, by the time it reaches here, the potential energy goes to 0. It's all kinetic energy there, and that's what does the work on the pile, driving it into the ground. Okay? What's that?
That would seriously hurt somebody.
Oh, you better believe it. Squash somebody. Yeah. All right. Okay. So the potential energy at the top would be what was the formula for potential energy? Gravitational potential energy? Oh boy, what was it? It's what? No, that's kinetic. Yeah. mgh. Perfect. Mass times acceleration due to gravity times whatever height it is to the top of that pile. Okay? Now, the kinetic energy at the top is 0 because it's at rest. It's not moving. Velocity is 0. But when you release it, and my book, is the second part of that figure is here. When you release it and it falls, just before it hits there, it's at its maximum kinetic energy. And what is that formula? 1/2 mass times velocity squared. Okay? Because down there you've reached your bottom of the height, so your 0 reference level, your potential energy is 0 down there. So what this leads us to, is this. The potential energy at the top, mgh, where the kinetic energy is 0, the sum of those is equal to the sum of these, which is all kinetic energy at the bottom. So we're going to equate those and put them equal to each other, because they are, okay? So the mgh at the top is equal to 1/2 mv squared at the bottom. Now notice here, you can divide out the m's. It didn't matter what the mass of that was. It does for how far you drop it, but for this purpose, the masses divide out. And if you're looking for velocity, which is what they're looking for here, what you do is multiply both sides by 2 because we don't like denominators, right? Okay, so you have v squared is equal to 2gh, and then how do you undo a square? Take the square root. So v is equal to the square root of 2gh. It doesn't matter how much what the mass was. The velocity is all a function of how high you dropped it from. Okay? And that's the formula you see at the bottom of the page here. V is equal to the square root of 2gh. Where v is in velocity, in meters per second, g is acceleration in meters per second squared, okay, and then h is in meters. So you have these are just the units here, meters per second squared times meters, that would be meters squared per second squared, and then when you take a square root, they go to meters per second, which is exactly what we measure velocity with, right? So yeah, the units check out, they work. Make sense? All right, let's do example 1, top of page 220. Okay, I'm going to erase, I'm having trouble seeing my icons down here. Okay, erase that, and I'll just use this space to write. Okay, pile driver falls freely from a height of 3.50 meters above the pile. So, I don't know, let's use this one. This height is, what did I say, 3.50? Yeah, 3.50 meters above the pile. Okay? What is the velocity as it hits the pile? Hey, they didn't give us the weight or the mass. You don't need it. How do you get velocity? What's that formula we just came up with? Square root of? Say again?
Oh, never mind.
We just got it. Unfortunately, I erased it. Square root of 2, no, G, H. Yeah. I feel like I have an echo in here. Yeah, okay. All right. All right. So the velocity at the bottom is going to be the square root of 2 times, and what's the G? Second? 9.80 meters per second squared. And by the way, remember that 2 is from the 1/2. It has as many significant digits as you want. That's just a raw number. It's not a measurement, okay? And what was the H? 3.50 meters, okay? So what does this turn out being? That would be 2 times 3.50 would be 7 times 9.8. That's going to be something about 60-something, right?
You have to do it in the square, right?
Yeah, you put it under the square root, right? Oh, you're putting all under there. That's fine. You can do that. So, okay. It's going to come out close to 8, isn't it?
8.28.
8.28.
25, you know, it's a long number.
8 point. Okay, give me 4 digits anyway.
8.282.
282. Okay, that's enough. Okay, so you count everything else is 3 digits. 3 digits. You know, everything's 3 digits. So you count 3. 1, 2, 3. Look to the right. 2. Throw it away. Less than 5. So it'd be 8.28. And what units? Here, yeah. Here you had meters squared per second squared. Take a square root of that, you get meters per second. Great unit for velocity. And let's see what they got. Oh boy, 8.28 meters per second. Make sense? Okay. All right. All right to move on? Okay. Now we go to our good old pendulum. Okay? Conservation of mechanical energy can also be illustrated by considering a swinging pendulum where there's no resistance involved. Now, you know there's always a little resistance, but we're going to minimize that. There's not enough to worry with. Okay? Now, excuse me, there's a little bit of problem with this because they have the angle so great. Sometimes you can't work at as high angles as you want to because there's other things involved here. But we're going to ignore the fact that they have it really way, way high. 65 degrees is pretty high there. Okay, but that's as high as you're going to do it. Now, where do you see pendulum? Where have you ever seen a pendulum?
Just like
At a clock, yeah.
clock.
Now, let's talk about what that pendulum is like. And that clock, was it enclosed with glass? Okay, that's to cut down air resistance. Remember, you're trying to minimize resistance. The other thing about it is that pendulum was big and round like this, right? But it was very thin this way. That way you minimize air resistance because it goes back. If it went like this, it'd be a lot of air resistance. But like this, very little air resistance. So they've done everything they can to minimize friction or air resistance. Now, you always have a little bit at the joint here. There's always a little bit of friction, just like there is in my sore shoulder here, but never mind. So, this one's much bigger angle than the pendulum and the clock. And this one's raising to 65 degrees, okay? But they stopped it right there. Now, here's the weight at the end. We're going to ignore the weight of this, just the weight at the end, okay? What kind of energy does that have? Second? Potential energy, because it's not moving. All of the energy is potential energy, gravitational potential energy. Whatever the mass is there, times the acceleration due to gravity, times the height above the bottom of the swing. Because it's not going to go any further than that, right? So whatever the distance here, that's how much it changed raised to there. That's your change of height, okay? Everything's potential energy. No kinetic energy because it's not moving. But then when you release it from there, what's it going to do? Start falling. Now it's going to start falling slowly at first, but then pick up speed, reach its maximum speed here, because once it gets here, it starts going up again, gaining potential energy, but losing kinetic energy until how high does it get over here? 65 degrees. This, if there's no friction, no air resistance, it goes back to 65 here. Now it's all potential, no kinetic. Then it stops here and then goes down, all kinetic, no potential, no kinetic. And in between, it's got some of both, right? Mechanical energy is conserved. Does not change. So up here, it's all potential energy, no kinetic energy. About midway, it's about half and half. Okay? Then when it gets to the bottom, it's all kinetic and no potential. Okay? Because you're at the zero reference level. And then when it gets up there, it goes back to all potential and no kinetic. Okay? And then it continues the action. Okay? So, yes, I think we have time to do example 2. Okay? Drop. Okay? Let me, yeah. All right. I think I'll go to a, what's that? Yeah. We may not do them all then. Okay. Let's discard this and go to back to this one and go to current slide and change our color back. Black. Okay. Drop a 5.000 kilogram mass. So here the mass is 5.000 kilograms. How many significant digits there? 4. Yeah. All 3 of those zeros are significant. And the 5, of course, is. Okay, from a hot air balloon 400 meters from the ground. So here we have our big old hot air balloon. And here you're in the basket, and you're dropping a 5 kilogram mass 400 meters to the ground. The H here is 400 meters, if I'm reading it right. Yeah. And it's 400.0 meters. How many significant digits there? 4 again. Okay, very good. Find its kinetic energy, its potential energy, and the sum of the kinetic and potential energies at 1 second intervals until the mass hits the ground. Yeah, we want to do that, don't we? All right. Now, let's start at the top. At the top, what kind of energy does it have? You're dropping it. So right before you drop it, what kind of energy does it have? All of its potential, because it's not moving at that point. So at the top, so we'll start at the top, and that would be 0 seconds. At 0 seconds, they put 0.00 seconds. So this will be the time, t measured in seconds. That's not t of s, but okay. The first column here is what is its height in meters from the ground.
Is 0 seconds?
Yeah.
0.
No, from the ground. It's up here in the hot air balloon, remember? 400. It's 400 meters above the ground. Okay? The next column is its velocity in meters per second. And what is it? Remember, you're dropping it right at 0 second. You haven't released it yet, so it's 0.000. Okay? No, I don't know. They only have... Oh, wait. You were right before. They're measuring the distance that's fallen. So S is measured downward, but positive, not negative. So you're right. They were calling it 0.0 meters. And they only call this 0.00 velocity. Why they're using different number of digits, I don't know. Okay, so let's now do E sub k. That's at the top, and that's measured in joules. What is the kinetic energy at the top? If it has 0 velocity? 0. How many did they put there? Just 0. Okay. What is E sub P at the top? Also measured in joules. All right. What you do here is mgh. This is mgh. Now the mass is 5, and the g is 9.80, and then the h is 400. Okay, so 5 times 400 would be 2,000 times 9.8. What does that come up being? That's 5.0. Second? 196 joules. Is that what they got? Oh, wait. I'm sorry. I was getting ahead of myself. They didn't do potential energy next. I'm trying to say it the same way the book does. Sorry. Come on. Here we go. Okay, the h, the height, I thought they had already done it. This is the distance it traveled. H is the height above the ground. This will be in meters too. And this will be 400 meters. And you don't really need 4 digits, okay? Because this, yeah, never mind. Okay. Okay, now they do E sub P, potential energy. And that's where you got your one, whoa, what are y'all telling me? 19,600. Okay, now they put a bar over there. I don't believe it. And here's why. Because remember the G here, even though you had 4 digits here, kilograms, you only had 9.80 meters per second squared. That's only 3 digits. You can't get 4 digits out of it. So lose the bar. Okay? Take off the bar there. Okay? 19,600. Okay? And then, and the last one was H was 400. And you don't need the extra 0.0 meters. Whoa! All right. And what's the total kinetic energy? Total mechanical energy? I'm going to call it ME, mechanical energy. That would be the 19,600 joules. All right. Oh, this will be in joules. Good deal. Thank you. Okay. All right. Okay. Let's do at least 1 second. Okay. Time equal 1 second. 1.0 seconds. Okay. Now, how far? Okay. How far has it fallen now? That's what S is. How far has it fallen?
400 meters.
Okay, no, that's how far it is above the ground. In 1 second, remember what 9.8 is? That's the acceleration per second. So it moves 9.8, it changes its speed 9.8 meters per second, okay? Now, they come up with a formula we haven't had yet. And this is where the S comes from. Sorry about this. S is equal to 1/2 GT squared. Okay? Now, I don't think we did that back in the last chapter. So I'll just have to give it to you. That's what the S is. So what you do is 1/2 of 9.8, that's 4.9, times 1 second squared, that would be 4.9 meters. Sorry about that. They hadn't given you that formula before, but that's where you get that one. Velocity. Now here's the velocity. You gain 9.8 meters a second each second, so that would be 9.80 meters per second. That's his velocity after 1 second, because that's how much the acceleration, it picked up that. And this is actually 4.90 meters. You have the extra zero there. Kinetic energy here is 1/2 mv squared. Okay? Oh, there's the mass. I forgot where the mass was. So to get the kinetic energy, 1/2 mv squared. So 1/2 of 5 times this velocity squared. Okay. Yeah, we're out of time. Now, here's what math teachers love to do. And the rest is left to the students, okay? No, we can pick up and start with this next time. We're not going to do the whole table, I guarantee. But we'll pick up from that and go from there, okay? We almost finished 8-4. Yeah. At least to do problems, that would be a great idea. Okay.
My math teacher can help you with this as well.
Well, possibly. I know the lab teachers, and some of them don't know physics that well, but some of them could. If you get the math for them, they can help you with the math part. They may not understand the physics part, depending on who you got. Yeah, depending on who you got. Some of them know it really well. I shouldn't have been recording that.